Okay, so 15.2 is acid-base definitions. So there are three different definitions for acid and bases. One is historical, one is only used in organic chemistry, and one is the traditional definition. So we're just going to briefly walk through each. So the Arrhenius acid and base definition is a historical definition. It dates back to the late 1880s. The Arrhenius acid and bases involve water. That is the key bullet point and thing you need to remember about these definitions. It involves water. So this gentleman, Arrhenius, noticed that when an acid or a base was added to water, it made a solution that conducted electricity. And if you recall back to the very first couple of slides of this chapter, we said that acids and bases can be added to a solution, a water solution, and they will make electrolytes or become electrolyte solutions, meaning to conduct electricity. So this is where that comes into play. So although ions weren't widely discussed or known about at this time, he basically concluded that this happened because of these wandering particles that eventually he named ions. And we know from 15.1 that when an acid or base ionizes in water, it does break apart into ions. So he was on the right track, and those ions, those charged particles, can conduct electricity. Okay, so the definition of an Arrhenius acid is a substance that adds H+ ions to water. So in this example, you have HCl, hydrochloric acid, plus water, and our products are H3O+, our hydronium ion, and our anion, chlorine. So basically he is saying that this definition, an acid will donate an H, a hydrogen, to water, and the results are ions that conduct electricity. So you've kind of already seen that. And his definition of a base is a substance that adds OH ions to water. This is a little bit of a different situation that you've seen, but just understand, remember, you can write H2O as HOH. So let me rewrite that for you. So remember, we can do H2O as HOH. So this is saying that the OH is added to water. So you get an OH minus in an aqueous solution. So it's similar to what you wrote before, but it just looks a little bit different because we weren't specifically talking about this definition. So those are the Arrhenius acid and base definitions. Very historical. Then we have our Lewis acid and base definition, named after this gentleman, Gilbert Newton Lewis. This is only going to be used in organic chemistry, so we will not be discussing it in our acid-base chapter, but it's a definition that does not involve water. So inorganic chemistry involves a lot of water. However, organic chemistry does not. So Lewis was studying organic chemistry, so he wanted a definition of an acid and base that didn't have to be in a water solution, because they don't necessarily have to be. So his do not involve any H+ or OH- ions, which come from water. So a Lewis acid basically accepts a pair of electrons, and a Lewis base donates. So you have a Lewis acid accepting electrons and a Lewis base donating. That's all you really need to know about that. And lastly, we have our most traditional and widely talked about definition of acid and base. This is the Bronsted-Lowry definition, named after two gentlemen. So they also wanted to develop a definition that didn't involve water, because once again, not all solutions are water-based. It can be any type of solution. However, they wanted something that was actually usable in other types of chemistry, whereas the Lewis acid base was only good for organic. So they said this is the most common, and I have Bl for Bronsted-Lowry. You can write the whole thing out if you would like to. So a Bronsted-Lowry acid can donate an H+ ion, and a Bronsted-Lowry base can accept an H+ ion. That's really all you need to know. So now we're not talking about acid plus water or acid plus base. I'm sorry. We're not talking about acid plus water or base plus water. There we go. We're talking about an acid plus a base. Okay? So in this case, we have an acid which has an H on it, and we have a base, whatever base that may be. The acid will donate its hydrogen to the base, and the base will accept it. So for example, if we had H2O plus NH3, water would actually be our Bronsted-Lowry acid. It got cut up down here, but it's an acid. And then our base would be ammonia. So the H on the acid is donated to the base. And remember, you can once again write H2O as HOH. So we're giving one H to ammonia. So now it's NH4 positive because it accepted an H. And that only leaves this OH left, which is a minus sign. So this is specifically when you have an acid plus a base, but the acid or base does not have to be water. It can be whatever it wants to be. Okay, so just some examples here of more specific Bronsted-Lowry examples because that is our most common. And I think I do use water in these, but like I said, you don't have to. So the first one, we have HCl plus H2O. Well, HCl is going to be our acid. I've labeled it A. The base is going to be water. As we just said, an H is donated from the acid to the base. The base accepts it. So we get H3O plus because the water accepted the H plus Cl minus. Okay, in this case, we don't have water. So we have ammonia, NH3 plus HCl. Well, HCl is our acid because it starts with H, hydrochloric acid. It doesn't matter the order. The acid now comes second. It will donate its hydrogen to the base. So now you get this H is being given to the base. You just get a chlorine ion, which is negative. It gave up a proton, if you will, with the H. And now you have NH4 plus because it accepted. Okay, what if we have H2O plus NH3? Well, NH3, once again, is ammonia. That's a base. That means water, in this case, has to stand as an acid. So acid will give to the base an H. We are left with NH4 plus OH minus. So the very first thing you have to do is label acid and base and then show the movement of that one H. Okay, and in this case, this is a weird one. I will not ask you this. Let's actually just pretend this one doesn't exist because it is complex and we're not going to go there. So I'll just get rid of that one. Pretend it doesn't exist. So here's just a chart explaining each of these two in kind of one format. Just know the general definition of them. Like I said, Arrhenius is going to involve water, H plus and OH minus, aqueous solutions. Lewis does not involve water. It is for organic chemistry and it's electrons either being donated or accepted. And then Bronsted-Lowry can involve water. It doesn't have to. We say proton donor or acceptor. Okay, and then a couple people asked me about this in class, but water is a good example of an amorphoteric solution or substance, basically something that can be an acid or a base, depending on the situation. Did I say that right? I'm not sure. Amphoteric. That's what we're talking about here. So here's some examples besides water. Water is definitely one, but here's just a couple other examples. Notice they're all charged ions. That's important. Water is not, but water is unique. So once again, just a substance that can behave as an acid or a base, water is the best example. So that ends 15.2. And real quick, I want to go into 15.3. So 15.3 is very short. It's just this slide. It is about neutralization reactions. So it's basically a reaction of an H plus ion and an OH minus ion, basically an acid and a base, involving those two ions. And your products are water and a salt. And this was also on the first couple slides in the chapter. So a salt in this case is any ionic compound from which a cation from the base and an anion from the acid joined together. So it doesn't have to be table salt. Like the example can be any metal and non-metal, a cation and an anion. So best example, hydrochloric acid plus sodium hydroxide yields water and a salt, specifically NaCl. So just so you understand, once again, we're going to put both of these into solution. They ionize. They break apart. The H joins with the OH. That's how we get water. The Cl from the acid becomes an anion. The metal from the base becomes a cation. Opposites attract, and you get NaCl. The metal always comes first, followed by the nonmetal. So once again, acid plus a base breaks apart. You're always going to get water, H2O, so that takes care of the H, and the OH. Whatever's left over combines together as ions to become a salt made of a metal and a nonmetal. So very brief information, but important. Skimming the surface here. This is the end of chapter 15 officially.